Now let us look at the next class. In this class we'll look at, so first let's look at what is the system of linear equations, and then we'll proceed. So recall that you have the system Ax is equal to B, where A is an m cross n matrix, X is n cross 1 vector of unknowns, B is m cross 1, so that it makes sense. So in general we write A as A11, A12, A1n, A21, A22, A2n, and AM1, AM2, AMN. So this is an m cross n matrix. X we will generally write it as x1, x2, xn, and B for us is B1, B2, Bn. All right, this is what we have. Fine. So according to this, the system Ax is equal to B, the matrix A, if you recall, it was called the coefficient matrix. And there was an augmented matrix. So I'll write it as also augmented matrix. Suppose I say it as AUG. That's the way I write, suppose AUG. Then AUG was nothing but A and B. Sometimes we wrote like this. Sometimes we may just write AB like this. All right. So depending on the requirement, we may keep changing our notations here and there. So don't worry about it. Either you can put a vertical line or you need not put the vertical line. But as soon as you have the coefficient matrix and the RHS, well, B is the RHS, then you have the augmented matrix. All right. So the important thing to understand in the augmented matrix is that augmented matrix has augmented, this AUG is a matrix of size or order, whatever you want to talk of, order m cross n plus 1. All right. So what are they? So if I want to understand it, so if I want to look at augmented matrix, it's a ith column, I for ith column here, then this consists of coefficients of the unknown xi whenever 1 is less than equal to I, less than equal to n, because n plus 1 corresponds to B. 2, augmented matrix, look at the n plus 1th column, then this is nothing but B, the RHS of the system Ax is equal to B. And then what about the rows? If I look at the jth row of A augmented matrix, then this is nothing but the jth equation of the system Ax is equal to B. So note that this corresponds to nothing but J is here. So AJ1 x1 plus AJ2 x2 plus AJN xn is equal to Bj. 1 is less than equal to J, less than equal to M. This is what the augmented matrix is. Fine. So you understand these notations. These are important notations that I would like you to recall and understand them. Fine. So definitions now. What is the solution of the system? Definition. A vector x naught belonging to say Cn or Rn, wherever we are looking at, is called a solution of the system of the linear system Ax is equal to B if A times x naught indeed equals B. All right, this is important that I multiply A to x naught, and if I look at the resultant should be my B. Fine, that's important for us. Well, this is one definition. Another definition that I would like you to know is that a system Ax is equal to B is said to be consistent. All right, consistent if Ax is equal to B has at least one solution. The system Ax is equal to B is called inconsistent if Ax is equal to B has no solution. So we've already looked at certain examples when it has solution, when it has not a solution, but let's look at some more example to have a better clarity of things. So let's see example. So the first example that I'm having got is this 3 cross 3 matrix in 3 unknowns. So I've got 1, 1, 4, 1, 4, 1, 1, 2, 1. This is my A. X, I'll write it as X. There are only 3 unknowns, so X, Y, Z. In place of X1, X2, X3, I'll write like this. And my B is going to be 1, 0, 1. And let's look at what does it represents when A is this, X is this, B is this. Then there are two ways of understanding it. One is through equations, as I said. So the one equation that I'm looking at here is X plus Y plus Z is 1. X plus 4Y plus 2Z is 0. And 4X plus Y plus Z is equal to 1. So this corresponds to the system Ax is equal to B. This is one way of looking at it. The other way to look at is nothing but look at 114 times X plus 141 times Y plus 121 times Z is 101. So there are two different representation of the system, homogeneous system Ax equal to B, of the system Ax is equal to B. This is one way, which is looking at the planes or lines, whatever you want to talk of, some things. Where I am looking at geometry, here I am looking at vectors and two systems that are there. Fine. So this is what is saying that the first column here corresponds to the coefficient of X. Look at here, X, 114 is here. Then the second column of the augmented matrix of the coefficient matrix is nothing but it comes with Y, and the third column comes with Z, and the right hand side is your B. Fine, this is what you have. I would like you to verify here that X, Y, Z, which is equal to 0, minus 1, 2 is a solution. Why it is a solution? Just plug in the value. So 114 times 0 plus 141 times minus 1 plus 121 times 2. This is equal to, just verify it. So this into this is 0, so this goes off. Minus 1 plus 2 is 1. 4 minus 4 is 0. And here it is 2 minus 1, that is 1. All right, so you can see that this is equal to B indeed. Fine. So therefore it is a solution, and therefore the above system Ax equal to B, the above system Ax is equal to B is consistent, and this is a solution, and X naught, which is equal to 0 minus 1 2 transpose, is a solution. This is one example. Another example, let us take A is equal to 1 1 1 2 and B is equal to 2 3. Then you can verify that this implies the system Ax is equal to B, where X is xy, has a solution X, which is 1 1. You can verify it. All right. So this system is also consistent. So consistent again. Ax is equal to b is consistent. Fine. Now let's look at another example 3. So here I'm going to look at two b's. All right, so a is say 1 2 and say 2 4. B for me is say 1 comma 3. Fine. Then in this case, if I look at Ax is equal to b, Ax is equal to b has no solution. Why it is no solution? Basically because you want to look at 1 2 times x plus 2 4 times y is equal to 1 3. So you can verify that. I have some issue here in the sense that the first equation, if I look at, says me x plus 2y is equal to 1. Second tells me that 2x plus 4y is 3. And these two together will imply that 0 times x plus 0 times y is equal to 1, which has no solution. No solution. And this implies that this system Ax equal to b is inconsistent. Fine. Another example that I would like you to look at is just A here itself, the same A. A is 1 2 2 4 and B is 7 comma 14. Then verify that A times, just look at here, multiply it by something here. So I want to multiply by 7 comma 0. So this is same as 1 2 2 4 times 7 0 is nothing but 7 times 1 2, which is 7 14, which is B. All right. So 7 0 is a solution. Similarly, you can verify that 0 and just multiply here, say 7 by 2 is, so this is equal to B, implies 0 comma 7 2 by 2 is another solution. So you can have more than one solution, and then not only more than one solution, you can see that if I look at the difference of these two, so look at the difference. So let u is equal to 7 0, v is equal to 0 comma 7 by 2, then define y is equal to u minus v. So this implies a times y is equal to au minus av, which is same as au is already b, av is also b, so this is 0. Implies u minus v, which is not a 0 vector, this is a solution of Ax is equal to 0. Here A that I have taken is 1 2 2 4. Fine. So starting with Ax is equal to b here, starting with Ax is equal to b, I have got a solution of the homogeneous system Ax is equal to 0, and this I have got with the idea that there are two solutions of the system Ax is equal to b. Fine. And note that u minus v is not 0, because u minus v is nothing but 7 and minus 7 by 2 for us. This is non-zero vector. Fine. So such a vector, such a solution is called a non-trivial solution. All right. So important definition. A non-zero solution of the system Ax equal to 0 is called a non-trivial solution. Very, very important. We'll be using this word non-trivial again and again after a few lectures. So you must keep track of that part. Fine. And the next thing that we would like to know is what is called a trivial solution. The solution x naught, which is the zero vector is called a trivial solution. All right. So as a remark, I would like you to understand these things. So remark one by one. So there are a few remarks that I would like you to understand. One, whenever we have two or more solutions of the system Ax is equal to B, then we always have a non-trivial solution of the corresponding homogeneous system Ax is equal to 0. All right. So two or more. When I say two or more, means they are distinct in some sense. All right. So you have U, you have V. U is not equal to V. Define, as I did earlier, define y is equal to U minus V. Then U minus y is not 0, and A of y is 0. Fine. So you get non-trivial solution of homogeneous system. Fine. Not only that, what you get here is that if I look at any C belonging to Cn, to complex number or to real number, then A times C of y is C times A of y, which is C times 0, which is 0, implies we get infinite number of solutions. We get infinite number of solutions. It's not only one, which is a non-trivial solution. Whenever y is non-zero, then C times y is also non-zero for C not equal to 0. And this is true for any C, so you get infinite number of solutions. This is very important. That is, whenever you have two solutions which are distinct of the system Ax is equal to B, then you have an infinite number of solution and a non-trivial solution, whatever you want to say, of the corresponding homogeneous system Ax is equal to B. All right, this is one thing. Another thing I would like you to understand is, so that if U and V are solutions and U is not equal to V, then A of U minus V is A minus V is equal to 0 as such. So U minus V is not a solution of Ax is equal to B. So in place of U minus V, I can look at the line. Well, U minus V is a vector, fine. So I can also look at this vector collection, alpha times U plus 1 minus alpha times V, alpha belonging to R or C, wherever you want to look at, fine. If I look at this, then this is a solution, this whole set, this is a solution of Ax is equal to B as A times alpha U plus 1 minus alpha V is same as alpha times AU plus 1 minus alpha times AV, which is alpha times B plus 1 minus alpha times B. Alpha B minus alpha B will cancel out. I will get it as B. All right. So there are infinite number of solutions of the system as such. Fine. And this represents the line joining the points U and V. All right. So U and V are vectors, but they also represent a point. And then look at that line or the position vectors and things like that that you know from whatever you have. So that's important. All right. The other thing that I would like you to recall from the whatever I have made is that whenever I have a system, I have any solution of the system Ax is equal to B has two forms. One is what is called, so I wrote y as U minus V, and so U and V are distinct here. So you can, from here you can say that U is nothing but y plus V. So you can say that any solution of Ax is equal to B is of the form so any solution of the system any solution of the system Ax equal to B is of the form x naught plus xh, where x naught is called a particular solution of particular solution of Ax is equal to B, and xh is called a solution of the corresponding homogeneous system. All right. So whenever we have a system, homogeneous system, fine. So you can always break it into two parts: a particular solution and a homogeneous solution. All right. So this is very, very important that I want you to understand. We have already looked at Ax equal to 0 and things like that. So I will end this lecture with the following idea that I want you to understand, that understanding these two sets, all x belonging to Rn or say Cn, such that Ax is equal to 0. This set is, we need to understand this set. This set is called null space of A. All right. And another set that we need to understand is, look at all B belonging to Rm or Cm, wherever you want to look at, such that Ax is equal to B has a solution. All right. So I need to understand these two things. For us, we'll do it afterwards, after maybe after a week or 2 weeks. All right. So the idea here that we have is, I have a function f from Rn to Rm or from Cn to Cm, and I define f of x as Ax. In this case, this part is looking at what are the points which are being sent to 0, and this is nothing but the image of the function f. All right, relating these two. So we'll be studying these two things after a few lectures, and this is the notion what are going to play very, very important role as soon as you come to vector spaces, linear span, linear combination, and things like that. All right. So understand, recall these things are very important. Other thing that I would like you to remember always, what is a non-trivial solution and what is a trivial solution. All right. So that's all in this lecture. Thank you.